Okay, so we started with this activity, change one letter at a time to get us the message that when we do proofs, we really have to break down our reasoning into one little step at a time. So when we do proofs, basically what we're going to do is we're going to start with algebraic proofs because you already know algebra. So it kind of gets your feet wet with the whole proof process with something you already know how to do. And then we're going to start doing geometric proofs. Okay, so here is an algebraic equation. What is the very first thing you would do to solve this equation if we were trying to solve for x? What would you do first? Yeah, we got to get rid of the parentheses first. So we're going to keep the negative x. And then to get rid of the parentheses, we have to do this multiplying by -2. What's it called? Good, the distributive property. So we're going to do -2 times 9 and get -18. And then -2 times -8x, negative times a negative is a positive 16x. And then we still keep the equals 12. So over on this side, see where it says reasons for each step? The reason is what you just told me this is, the distributive property. So we're just going to write that here. This is our reason, distributive property. Okay. All right, now what would you do next? What would be the next thing you would do? Yeah, so you would basically, that's called combining like terms. There's an x and an x, and we're going to combine them together. So we're going to get 15x minus 18 equals 12. Okay, so putting those x's together is called combining like terms. So that's our reason. Combine like terms. All right, so now we have 15x minus 18 equals 12. What are we going to do next if we're trying to get x by itself? Yep. Good. Add 18. We're going to think about it as adding 18 to both sides. So add 18 here, add 18 here. We got two sides of this equation. It cancels out here. We're left with 15x equals 12 plus 18 is 30. So what did we do? Add 18 to both sides. Yep. And we're going to see that's called the addition property. Okay, the next thing we do, divide by 15 on both sides. And finally, we have x equals 2. Oops. And basically that was just division. We divided by 15 on both sides. So a proof is a convincing argument that uses deductive reasoning. Again, we're starting with algebra because you know how to do that. You were able to give me all of the reasons there. And that's what I mean by, you already know how to do that, right? You were able to know exactly what step came next. So a couple of the properties that we are going to be using, distributive property, which basically you guys already know, you distribute by multiplying through the parentheses by whatever's on the outside. So if it's addition, it's AB plus AC. If it's subtraction, it's going to be AB minus AC. Good. And then combining like terms, remember that means, like terms means you have to be the exact same combination of variables. So only you can add x's to x's. So 2x plus 3x would be what? 5x. Can you add 2x plus 3x squared? No. Can you add 2x plus 5y? No. Okay, so it has to be exactly the same terms. All right, so if you turn the page, we have this chart that shows you all of the other possible algebraic reasons in a proof. Most of them are properties of equality. That just means that it keeps the equation equal. So when you add both sides by like 18 like we did, it's still equal because we did it to both sides, right? So it's a property of equality. So addition property of equality just basically says you can add the same thing to both sides of an equation and it maintains the equal value of the equation. Subtraction property just says you can subtract the same thing from both sides. Multiplication property just says you can multiply both sides by the same value and it'll still be equal. And division says you can divide both sides by the same value and it will be equal. Okay, the substitution property of equality, you've done this before. You might not have called it that, but whenever, if I gave you like an expression like x plus 5, I might have said evaluate when x equals 3. Well, what would you do then? What would you do with that 3? Plug it in for x. Exactly. So because this says that x is exactly equal to 3, that means wherever there's an x, we could put a 3 because they're exactly equal. So we can like, just like quick change. One can replace the other one because they're exactly the same. All right? So in this equation then, we could just get rid of the x. Oops, crossing out an x makes it still look like an x. And put a 3. And then this becomes 3 plus 5. And that's 8. So what the property of substitution property of equality says is that if A equals B, then B can replace A in any expression. In other words, wherever there's a B, you could put an A. Just like we said, wherever there's an X, you could put a 3. Now, there's two very important statements. So these two statements are going to make more sense later when we're doing more proofs. I'll mention them now, but we're going to mention them again later when they will make more sense. But it's important to remember that the substitution property can only be used in equations. Now, all of these properties of equality can really only be used in equations, but I'm specifically pointing out substitution property because often people want to substitute things that aren't equations, but you have to remember it's a property of equality. It has to be in equations. It can't be in a congruent statement. It can't be in a sentence. It has to be in an equation. It has to have an actual equal sign. All right, so that's something to remember for later. Also, notice that if two expressions are equal to the same value, then the two expressions can be set equal to each other by substitution. And again, that will make more sense when we run across that in a proof. Okay, two more properties. Reflexive property. This property might seem so obvious, you're going to think, why do we even have to call it something? Because it basically says A equals A. Like, duh. We all know A equals A. We all know 2 equals 2. Why do we have to have a reflexive property? Well, the reason is in proofs, you have to explain every single step. And although algebraic proofs are not going to have much reflexive property, there are geometric proofs that are going to require it. So it's kind of one of those things we learn now, we kind of put it on the back burner, and we're going to use it a lot more later. All right? Transitive property of equality. This says if A equals B and B equals C, then A must equal C. Think about it this way. If I'm the same height as my sister, and my sister's the same height as my mother, then what do you know about me and my mother? Must be the same height, right? Because basically you're saying that all of them are equal, right? So that's called the transitive property. It's like a transition. It's like you're hopping from one to the next, and then you're transitioning the first to the last. And we always use A, B, and C here, but keep in mind that transitive property could be A equals B, and B equals C, and C equals D, and D equals E. So A equals E, right? There can be a longer string of transitioning. If I'm the same height as my sister, and my sister's the same height as my mother, and my mother's the same height as my cousin, and my cousin's the same height as my aunt, and my aunt's the same height as my grandmother, well, then I must be the same height as my grandmother, right? It's just basically you're saying everything's equal, okay? Okay. So there are two ways that we're going to write proofs. Two-column proofs and flowchart proofs. Okay, so the two-column proofs are more traditional. They look like this. We are going to mostly be focusing on flowchart proofs. All right, so there's two types of proofs. We are going to be focusing on flowchart proofs, which is on the right-hand side here, but two-column proofs are actually probably better when you're writing algebraic proofs, just because it's just like what we just did, that algebra problem. On the left, you got the the problem worked out, and on the right, you've got the reasons, and it sort of just makes sense that way. We're still going to practice both with algebraic, but eventually the geometric proofs make a little more sense with the flowchart. So that's really what we're heading to. Okay. You can see that this is just like the problem we just did, right? It's exactly what we did. It's just in this two-column format where at the top of one column you label it statements, and at the top of the other column you label it reasons. It will be written like this: given the first statement, prove, and then whatever you're trying to get to. In this case, we're trying to prove that x equals 2. And then you can see these are all the steps that we already just talked about, right? Instead of saying add 18 to both sides, you call it the addition property of equality and division property of equality. Okay, so a flowchart proof looks kind of like this. Your first step is your given, your last step is still what you're trying to get to, and basically you're putting things in boxes, and you put the reason right under the box. Instead of two columns, you just have this flowchart. You guys seen a flowchart before? Like at all in general, a flowchart? They're pointing from one box, pointing to another box means that that box leads you to that next box. Okay, so the arrows are actually really important. All right, so let's turn the page. This next page is just full of information. Basically, you can refer back to this. Parts of a two-column proof. You're going to have your given, your proof. Sometimes you have a diagram also. Not with an algebraic proof, but with a geometric proof, often you're going to have a diagram. Then you have your two columns. You got to make sure you label them. Your given goes first. Your proof should be your last statement. Notice your last statement's reason is never proof. although your first statement's reason is given. Okay, so never, ever, ever write the word prove as a reason. That's not a reason. Okay. I just want to point out that these should be numbered, and these numbers seem to have gotten messed up. But all of these numbers should match, the statement column should match the reason column. Okay. Flowchart proofs, again, this is an explanation of a flowchart proof, but I'm going to take you through one so that it will make more sense. This is a good box to kind of refer back to, you know, as you're doing your homework and you're like, wait a minute, what do I do next? So here's where you would kind of look for that. Okay. This box is full of definitions that you should already know. Okay? Perpendicular lines. Lines that come together to form right angles. You should have learned that in middle school. Right? Acute, an angle between 0 and 90. A right angle is a 90-degree angle. Obtuse, between 90 and 180. A straight angle equals 180. Complementary angles, two angles that add up to 90. Supplementary, two angles that add up to 180. Vertical angles we've learned already in all your last tests, right? Two angles whose sides are opposite rays. That's one way to explain it. Just remember that it looks like this, right? Vertical angles. Vertical angles theorem says that if they're vertical angles, then they're congruent. Adjacent angles you talked about and you learned on for your last test, right? Right next to each other, common side, common vertex, don't overlap. The angle addition postulate is with adjacent angles, one little angle plus the other angle right next to it equals the whole angle. Linear pair are a pair of angles, two angles that sit on a line basically. And then the linear pair postulate says that if they do form a linear pair, then they're supplementary. All that sound familiar to you? Yes. Okay. So these are also going to become reasons in our proofs. Okay? All right. So those can be reasons also. Definitions and theorems can be reasons as well. All right, so if you turn the page then, the vertical angles theorem, just a reminder, if two angles are vertical angles, then they are congruent. And just to make sure we all understand what congruent means, congruent angles are angles that have equal measures. So both of these can be reasons in a proof as well. Often, oh my gosh, this is not even the final version. Does yours say that or something else? Yes. I don't know what happened to my final version. Okay. You should have like definition of congruent. Is also a reason in a proof. It's actually a really common reason in a proof. And it's whenever you're turning something from equal into congruent or congruent into equal. Again, I know a lot of this is going to make more sense once we start doing them. So I'm actually going to skip us down to here. Let's do some quick geometric proofs. Like this is just really part of a proof. It's not a whole proof, just part of a proof. Basically, we're just giving reasons. So right here, if angle 3 and angle 4 form a linear pair, then angle 3 and angle 4 are supplementary. What would be the reason, do you think, angle 3 and angle 4 form a linear pair? Therefore, angle 3 and angle 4 are supplementary. What do we have that says if two angles form a linear pair, then they're supplementary? Yep. Perfect. So your reason, if that was stated in a proof, would be linear pair postulate. All right, let's look at the next one. If angle 5 and angle 6 are complementary, then the measure of angle 5 plus the measure of angle 6 equals 90 degrees. So think to yourself, if I said to you, hey, 5 and 6 are complementary, and you thought to yourself, aha, that means they add up to 90. What is it from that list that you knew in order to make that statement? What did you know the definition of? I'll give you a hint. It's a definition. If I say to you, 5 and 6 are complementary, and you say, oh, so 5 and 6 must add up to 90, what do you know the definition of? Yeah. Exactly. So that would be your reason in the proof. Definition of complementary. All right. So this one is sort of similar because it's just a definition, something you know what it means. If angle 7 is a right angle, then the measure of angle 7 equals 90 degrees. What do you know the definition of if you can make that statement? So I say to you, hey, angle 7 is a right angle. And you say, oh, okay, then it must equal 90. What do you know the definition of? Well, yep, so definition of right angle. You know what a right angle is, so you know the definition of right angle. Okay, given this diagram, you look at the diagram and you say, oh, okay, based on that diagram, I can see that the measure of angle 8 plus the measure of angle 9 is going to equal the measure of angle ABC. What is that we learned? This little angle plus that little angle equals the whole angle. Alex? Perfect. Yep, angle addition postulate. Okay, so these were given in sort of if-then form. In a proof, it would be sort of one step after the other, whether it's in a 2-column proof, it would be step 1 would be 3 and 4 form a linear pair, and step 2 would be 3 and 4 supplementary. If it's flow chart, it would be like this, right? Angle 3 and angle 4 are a linear pair, and it would lead you to say angle 3 and angle 4 are supplementary. So it's written as an if-then statement, but understand that in a proof, it would be one step after the other. Like, knowing the first step, it leads you to conclude the second step. So if you look back up a little bit to this box, and again, this is going to be a box also. All these boxes with little dotted, dashes around them, you can think of them as, refer back to these boxes. They're going to help you when you get stuck on proofs. So these are what we call kind of the common combinations. When you're dealing with linear pairs, often you have a statement that just says they're a linear pair. This is an optional statement. I think I even put optional on yours. Right? You don't have to state that it is a linear pair, but sometimes you'll see that they do. It's a good step to put in, but it's not absolutely necessary. Then you would have a statement that 1 and 2 are supplementary. That's the linear pair postulate. Notice that the linear pair postulate does not say if 2 angles form a linear pair, then they add up to 180. It does say that they're supplementary. So the best format, putting it into your proof, if you want to be really accurate, you first have to state that they're supplementary by the postulate. Then you have to say, okay, that means they add up to 180 because of the definition of supplementary. So this is a common combination. You're going to see the linear pair postulate with the word supplementary, and then add to 180 by the definition. Okay? And this is a common combination also. When you have angle addition postulate, you really need to use the names of the angles, all three of them. So like we did that last one, angle 8 plus angle 9 equals angle ABC. Here, measure of angle MRN plus measure of angle NRT equals the measure of angle MRT. You have to use all of those names of the angles first. That's the angle addition postulate. Then, just like you did on your last test, right, then you want to substitute in the values. Well, I know what MRN is. MRN is 2G minus 2, so I put that there. I know what NRT is. That's this one. And I know what MRT is. That's this one. So you're basically substituting. We take the 1 and we substitute it for what we know is equal to it. Okay? And then again, vertical angles, this is another combination. Again, optional to say that they are vertical angles by definition. But then the theorem, vertical angles theorem, says the two angles are congruent. So if they're congruent, we're using the theorem. Then sometimes it's necessary to turn that into a statement saying, well, if they're congruent, that means they're equal. So then you have the measure of angle 1 equals the measure of angle 3 by definition of congruent. Notice the difference here too. Okay, this just has an angle symbol. We're saying the angles are congruent. When you turn it into an equal sign, you have to have the little m's, right? Measure of. If you have them in an equation, you need the measure of. All right, so let's write some proofs. So for the first few, we're going to do them first as a 2-column and then as flowchart. Like I said, eventually we're just going to transition into all flowchart. All right, so this one has a given as the measure of angle 1 equals x and the measure of angle 3 equals 56. I would like to mention here that I still want you to, first thing, label the diagram. That's the first thing I want you to do. So take the given information and put it onto your diagram. Write yourself a note. Label the diagrams. That's going to be really important. Okay, so we're going to take the measure of angle 1 is x. Here's angle 1. I'm going to put an x right there. The measure of angle 3 is 56. So right away, once you're labeling your diagram, you should be thinking, aha, I'm dealing with what kind of angles here? Vertical angles. So that labeling of the diagram gives you a little sense of what you're dealing with here. Okay, in a 2-column proof, the first thing you're going to do is just list all the givens. You can put them all in one step. Okay, if we're dealing with vertical angles, what do we know about them? They are congruent to each other. Good. So by the vertical angles theorem, we're going to say angle 1 is congruent to angle 3 because they're vertical angles, so they're congruent by the theorem. Now my next step, the reason is definition of congruent. So we said we're going to use that to turn congruence into equals or equals into congruence. In this case, we have congruence. We want to turn it into equals. So what's my next step going to say? If angle 1 is congruent to angle 3, then what? Equal. Then we're going to say the measure of angle 1 equals the measure of angle 3. Right? So definition of congruent as a reason is always going to turn a congruent statement into measures being equal, or vice versa. could go the other direction. All right, well now we have that the measure of angle 1 equals the measure of angle 3. And if you look at the given, we can see that the measure of angle 1 equals x. And we can see that the measure of angle 3 equals 56. That means if they're equal, by substitution property, wherever there's a measure of angle 1, we could replace it with an x. That's my little sound effect for substitution property. Take one out, put one in, just replace them. Okay, so measure of angle 1 is written here in our equation. We can kick that out and replace it with what's equal to it. So we're going to put an x. Measure of angle 3 is equal to 56, so we can replace it with a 56. And then we just carry the equal sign down. So x equals 56, that's what we were trying to get to. That's our proof statement. That's how we know we're done. We do need a reason, though. X equals 56. What did I do here? What did I do? The whoosh-whoosh method, right? Substitution. Substitution property. You just replaced one or substituted one for another. POE is sometimes how we abbreviate property of equality. Okay, let's do that same proof as a flowchart. You'll see kind of the difference in our process here. Okay, so the measure of angle 1 equals x, and the measure of angle 3 equals 56. We put those all in one step when we had a 2-column. When you have a flowchart, you want to separate them. They each get put into their own box. Measure of angle 1 equals x is one given. The measure of angle 3 equals 56 is another given. Because sometimes you need to use givens for separate reasons. Now, over here, basically by looking at our diagram and labeling it, we can relate these angles. So this is where you would want to say, you know, angle 1 and angle 3 are vertical angles, or, and that's the optional step, or you could skip straight to angle 1 is congruent to angle 3. I can tell this by looking at my diagram and seeing that they're vertical angles. So knowing that my proof has an equal sign in it, I know that I have to get this congruence into a statement of things being equal. So if angle 1 is congruent to angle 3, then the measure of angle 1 is equal to the measure of angle 3. What's my reason here? If they're congruent, then they're equal. What's my reason? Good. Definition of congruent angles. Or just definition of congruent. I'll take that too. Definition of congruent. Notice so far our reasons match exactly what we had up here. It's just a different format. Okay, so now look what's happening. We are going to take this statement that angle 1 equals x, and this statement that angle 3 equals 56, and this statement, and we're going to combine them all together. Right? So we're basically using this equation, and we're replacing that. We're going to kick, actually, let me not put an arrow. It looks like I'm making a flowchart. But we're basically going to kick this out and replace it with an x, and we're going to kick this out and replace it with a 56. That's what we're going to do here. So x equals 56. But notice there's 3 arrows coming here because I needed all of this information to be able to make that statement. I needed this equation to substitute into, and I needed these two to know what to replace with what. So they all combined to get x equals 56. What is my reason there? What did I do? Yes, substitution. Good. Okay. Again, substitution property can only be used with equations. So that's why we had to kind of turn our vertical angle theorem into measures being equal before we could use substitution. Here we go. We're going to do just a flowchart for starters here. Again, that's what we're leaning towards. You know, eventually we're going to do all flowchart. So what are we going to put in this first box? What do you think we're going to put in this first box? Yep. Good. And what's going to go here? Yep. Each given gets its own box. Now, we want to make sure we label the diagram, but they actually did that for us here. 2x plus 30 goes in this angle, and x goes in the other angle. So now you're looking at your diagram, and you're thinking, aha, I'm dealing with what here? A linear pair. Very good, a linear pair. So we're going to use the linear pair postulate, which says if two angles form a linear pair, then they are supplementary. Good. So we're going to use the linear pair postulate to say angle AOM and angle MOC are supplementary. And that's the linear pair postulate. Again, I can see that I'm trying to prove that x equals 50, so I know I'm going to have to do some algebra, so I know I'm going to need an equation. I got to get this word supplementary into some sort of equation. What do you know about supplementary angles? They add up to 180. Good. So we're going to turn this word, this sentence basically, into an equation. Measure of angle AOM plus the measure of angle MOC equals 180 degrees. What is the reason? I'll give you a hint. Definition of good. Very good. Supplementary. All right, what's this equation going to be? This next box. How am I going to use the fact that measure of angle AOM plus measure of angle MOC equals 180? See this arrow, and this arrow. What equation am I going to write here, Jack? Perfect. Which is what you would have done on your last test, right? You would have written that equation and been ready to solve it. Now we're just breaking it down into giving it reasons, explaining every single step. What would be the reason for writing that equation now? Yep. Good. Substitution. We just substituted in what we knew each thing was equal to. The rest of the boxes here are just going to be doing the algebra. So, what's the first thing we need to do to get x? Good. 2x plus x is 3x. And again, you don't want to do more than one step at a time. I know sometimes it's tempting to, move the 30 over at the same time or whatever, but remember that cat dog, one thing at a time. So combine like terms first, then what? Yep, we're going to subtract 30 from both sides. The difference here is we're not going to actually show the subtraction, we're just going to show the result. If we subtract 30 from both sides, we're going to get 3x equals 150. Our reason? Subtraction. Again, you can use POE for property of equality. Then what? We want to get x to be 50. So what do we got to do next? Divide by 3, right? So x equals 50 by the division property of equality. Dividing both sides by 3. I'm going to skip over the 2-column proof of that same exact thing because I think you could probably figure that out on your own. And I'm going to go to number 7, where now we're just writing a proof. There are no boxes to fill in. You've got to draw the boxes yourself. Okay? So let's follow our steps. First thing we want to do is label the diagram. Right? So label the diagram first. Okay, so we're going to make a flowchart proof here. When you're labeling your diagram, what postulate do you think we're going to be using here? Perfect. Angle addition postulate, right? We basically know 3 postulates and theorems now. Linear pairs, vertical angles, and angle addition. This one is not linear pair, it's not vertical angles, but it is angle addition because it's 2 adjacent angles. So eventually, you're probably picturing in your head what equation you're going to end up writing, because you did that on your last test, right? But we have to break it down now into our flowchart proof steps. So basically, take each given, measure of angle 8 equals 14x minus 12. Put a box around it. Measure of angle 9 equals 4x plus 4. Put a box around it. Measure of angle ABC equals 17x minus 1. Put a box around it. Now, under each box, we're going to write our reason. All of those reasons are just given. So now we're going to kind of go to our diagram and say, okay, I think I'm going to be using angle addition postulate here. What would be the statement you could make where the reason is angle addition postulate? Be careful here now. Don't substitute yet. Angle addition postulate. We want to actually use the names of the angles. So what's this statement going to say? Is that a hand up? No? Is that a hand up? Okay. Okay, you could state that, but you don't need to. I don't want to complicate it. So what would be the next thing you would be able to say to get us closer to an equation? Perfect, yep. But we're going to have little m's, so measure of angle 8 plus the measure of angle 9 equals the measure of angle ABC. Now, notice you could call this angle CBA, but since they called it ABC, you want to kind of stick to what they used. Measure of angle 8 plus measure of angle 9 equals the measure of angle ABC, and underneath that, we're going to write our reason, which is good, angle addition postulate. Okay, now we're going to use all of these boxes to write our equation. What's the reason for that equation at this point in the proof? Good, substitution. Okay, I'm going to let you finish that. Okay, so you might have gotten to this point now, hopefully, right? Just doing the algebra, you get x equals 7. Combine like terms, subtract, add. You might have done it in a different order, but probably your steps are still going to be those 3 steps, okay? But that's not what we're proving. It says prove that the measure of angle ABC equals 118. If this was your last test before we thought about proofs, how would you then show that find the measure of angle ABC? What would you do once you have x? Yep. Plug in 7 for x into this equation right here, right? Because that's the measure of angle ABC. So we're going to do that. We're going to do exactly that. I'm kind of running out of room here, so I'm going to pull it to the side a little bit. And I'm going to take the measure of angle ABC equals 17x minus 1. I'm going to write it as 17 times 7 minus 1. What did I do? What might be my reason there? Substitution, exactly. I took out the x and I replaced it with the 7, and that's substitution. All right, so now we got to stop and think to ourselves, well, how did I do that? What boxes did I use? Well, I used this box that I underlined in red, so I'm going to put an arrow because I used that information to fill in this new box. What other box did I use? Yeah, x equals 7. This is the other box I used, right? Because that's what I substituted in. So those are the 2 arrows that you should draw to this new box. Now, once you've done the substitution, it might take a few steps to like simplify that, but I don't need you to write out all these steps. Once you get to the point where you've substituted in for x, you can just now say the measure of angle ABC equals, what was it, 116? 118? And for your reason, you can just say simplify. Okay. I'm actually going to skip to the back. I think we only have time to do one more here. So we're going to start with our flow chart. Let's just write this out. Measure of angle 4 plus measure of angle 6 equals 180. Given. And that's our only given. Look at our diagram. We can't really label it because it's an equation they're telling us, but I'm just going to mark angle 4 and angle 6. These are the 2 angles that they've given me that add up to 180. Don't mark them congruent. You don't want to put like an arch in both of them because they're not congruent to each other. I'm just kind of indicating on my diagram so I know what angles I'm looking at. Do we have a name for those 2 angles? Like, have we learned that that's a special angle pair? No. But is there a special angle pair in this diagram that we could label? Yeah, angle 4 and angle 5 are what? Okay, so they're supplementary. They're also adjacent, which makes them a linear pair. So if I say they're supplementary, I'm using the linear pair postulate. Exactly. So you can see how you're given some information, but you're also given this diagram. And from the diagram, you can conclude some information, which becomes statements in your proof. All right, so 4 and 5 are supplementary. What would be the next thing I can write from there? If they're supplementary, what does that mean? Yep. They add up to 180. So measure of angle 4 plus measure of angle 5 equals 180. Reason, definition of 4 and 5 are supplementary. Oh, that means they add up to 180. What do I know the definition of? Supplementary. This was one of our common combinations, if you remember. Okay, now, this is that second starred statement that I said this will make more sense later. When you have two things, two statements that are both equal to the same value. You see here this is equal to 180 and this here is equal to 180. They're both equal to the same value. Then you can set these two equal to each other by substitution. So you're going to say measure of angle 4 plus measure of angle 6 equals the measure of angle 4 plus the measure of angle 5. By substitution. Do you see what I did there? I used this part and put it equal to this part because they're both equal to 180, so I can put them equal to each other. I'm trying to prove that measure of angle 5 equals the measure of angle 6. Well, all I have to do now is get rid of this, and I have my reason. I mean my answer. So what I'm going to do is put the measure of angle 6 equals the measure of angle 5. And what did I do to both sides? I subtracted. I subtracted a measure of angle 4 from each side. Minus measure of angle 4. Okay, now I'm just going to go back to that proof that we skipped down here and do this out so that you have it if you need to refer to it. So here we have angle 1 and angle 2 are supplementary. That's one given, gets its own box. And then measure of angle 1 equals 7x minus 2, also given. And measure of angle 2 equals 17x minus 10, also given. So notice this one's a little different because there's no diagram. We're not looking at a diagram and saying, oh, what's the relationship from this diagram that I see? Instead, they give you this given that tells you the relationship of the two equations, the two angles. So knowing that they're supplementary leads us to be able to say the measure of angle 1 plus the measure of angle 2 equals 180 degrees. And again, if somebody tells you two angles are supplementary and in your head you know they equal 180, that's because you know the definition of supplementary. So now we have an equation. I know we're trying to prove x equals 8, which is, our clue that we're going to need an equation. So we've got all the information we need to be able to substitute. We're going to take measure of angle 1 equals 7x minus 2 plus 17x minus 10 for the measure of angle 2, and we're going to put it equal to 180 because we know they're supplementary, and we're using all three of these boxes here. So we have 3 arrows pointing to our new equation. From here it's just algebra. We're going to combine like terms. And then we're going to add 12 to both sides. Again, you just write the result of doing that addition. So addition, property of equality. Then we need to divide by 24 on both sides, and we get x equals 8. Dividing on both sides is the division property of equality. And x equals 8 is what we were trying to prove. We have a reason, so we're done. Okay, that's it. The best way to get better at proofs is just to practice, practice, practice. The more proofs you do, the better you get at it. Thank you.